In this video, we're going to talk about the Clausius-Clapeyron equation and the Antoine equation. First, where does the Clausius-Clapeyron equation come from? The Clapeyron equation relates the slope of a reaction line on a phase diagram to fundamental thermodynamic properties. So, we have the slope of a phase diagram, which is dp over dt, and since the system is at equilibrium, we know that the Gibbs energy of the component at the alpha phase and the Gibbs energy of the component at the beta phase are the same. So we have the following equation. Then, with Maxwell relations, we express the previous equation with the following variables. And knowing that the entropy is equal to the difference of enthalpy over the temperature, we relate both equations and we end up with the Clapeyron equation, which we can use to analyze the phase boundaries in a phase diagram. Let's begin with the solid-liquid boundary. For this process, the fusion enthalpy is used in the equation, and its value is going to be positive because it is an endothermic process. Then, the change in volume is going to be positive and is not going to be very large, since the component in both phases has a fixed volume. The only difference is that the liquid changes its shape to fill the container where it is located. So, the boundary line will be positive and large. Now, assuming that the change in volume is constant because it's very small, we integrate the equation and then we can clear the pressure 2 or the temperature 2. We can calculate the melting temperature of the component at a new pressure or the pressure at a new melting temperature. Now, let's analyze the liquid-vapor boundary. For this process, the enthalpy used is the one of vaporization, which is positive because it is an endothermic process. The change in volume is large and positive, because the component in the liquid phase has a fixed volume, whereas in the vapor phase, the component occupies the whole space where it is contained. So, the slope of the boundary is positive, but not as large as in the solid-liquid boundary. If we express the volume in the Clapeyron equation in terms of the ideal gas equation, we will have the following equation. And if we integrate it, we will end up with this equation, which is the Clausius-Clapeyron equation. Just like in the previous equation from the solid-liquid boundary, we can calculate a new boiling temperature at a certain pressure or a new saturation pressure at a determined boiling temperature. This equation is only valid when we're working with liquid and vapor. If we're working with solid and liquid, we have to use the equation obtained previously. Let's take another look to the Clausius-Clapeyron equation. With some mathematical modifications, we obtain a new form of the equation. This is the Antoine equation, which is easier to solve and takes into account the change of the heat of vaporization with temperature. Due to the characteristics of the Antoine equation, it has application in different areas. For example, in the pharmaceutical industry, this equation is applied in the pre-formulation studies, which focus on the physicochemical properties of a new drug candidate that could affect the drug performance and the development of dosage form. Currently, the Antoine equation is being applied in the study of nicotinic acid to see if it is a vitamin that can be manufactured into a tablet or capsule. In the additional reading section, there will be a link to Duncan Craig's book, Thermal Analysis of Pharmaceuticals, where there is a more detailed explanation of the application of the Antoine equation in the pharmaceutical field.